Welcome back. Now that we've learned RNN forward propagation using our example, I love movies, let's understand how an RNN actually learns, through backpropagation through time, or BPTT. This is how the network adjusts its weights to make better predictions. Quick recap. In forward propagation, we converted love movies into vectors x1, x2, x3. We computed hidden states h1, h2, h3, then predicted y-hat, and calculated the loss. Now, backpropagation works in the opposite direction, flowing from the loss, backward through the network. Why do we need backpropagation? Forward propagation only gives us a prediction and a loss value. To actually improve the network, we need to know how much each weight contributed to that error, and adjust them in the right direction. That's exactly what backpropagation calculates. Before we touch any formula, let's understand chain rule in plain English using a simple example. Imagine, 1 extra hour of sleep increases your energy by 2 units. 1 extra unit of energy increases your focus by 3 units. 1 extra unit of focus reduces your mistakes by half a unit. So, how much do your mistakes drop if you sleep 1 extra hour? You simply multiply the effects, 2 times 3 times 0.5, which equals 3. That's it. That multiplication of small effects, chained together, is the entire chain rule. Now let's see the same idea written with neural network terms. Backpropagation is built entirely on the chain rule. If a small change in a weight affects the hidden state, which affects the prediction, which affects the loss, the chain rule lets us multiply these effects together to find out exactly how that weight affects the final loss. Tap each circle to see what it means. Let's start at the very end, with the loss. Since we used cross-entropy loss together with a sigmoid output, something beautiful happens. The derivative of the loss with respect to the pre-activation simplifies to just y-hat minus y. Think of it as the gap between the prediction and the actual answer. This simple expression is the starting point for our entire backward pass. Using this, we can now find the gradients for our output weights. The gradient for y is y-hat minus y, multiplied by h3 transpose. And the gradient for the output bias, is simply y-hat minus y. Now here's the key idea of BPTT. Since the same weights, wxh and wh, are reused at every time step during forward propagation, their gradients must be calculated at every time step too, and then added together. Tap on any term to see what it means. Let's begin backward at h3. The gradient flowing into h3 comes directly from the output layer. It's calculated as y-hat minus y, multiplied by y transpose. This tells us how much the final hidden state contributed to the error. Before we can go further back, we need one more tool, the derivative of tanh. Look at this graph. The orange curve is tanh itself, it flattens out near +1 and -1. The red curve is its derivative, notice it's tallest at the center and almost flat, near 0, at the edges. That flat part is exactly where gradients start to vanish. At time step 3, we combine the incoming gradient with the tanh derivative to get the local gradient, often written as delta 3. This delta is then used to compute the gradient contributions to wxh and wh at this time step. Now the gradient continues backward to h2. It receives a contribution from h3 through wh. We multiply delta 3 by wh transpose, apply the tanh derivative again, and get delta 2. This delta also adds to our wxh and wh gradients. Finally, the gradient reaches h1, our very first hidden state. Same process, delta 2 multiplied by wh transpose, then the tanh derivative, gives us delta 1. Since H1 has no previous hidden state, the chain stops here. Here's the most important part of BPTT. Because WXH and WH are shared across all 3 time steps, we don't just use one delta. We add up the contributions from delta 1, delta 2, and delta 3 to get the final gradients for WXH and WH. Now, an important challenge with RNNs. Since we keep multiplying by WH and the tanh derivative at every step going backward, over many time steps these gradients can shrink towards zero. Look at this bar chart. The gradient starts strong near the output, but shrinks the further back it travels. This is called the vanishing gradient problem. Now that we understand vanishing gradients, let's talk about the broader disadvantages of RNNs. First, vanishing and exploding gradients make long-range learning unreliable. Second, RNNs process one time step at a time, so training is slow. We can't parallelize across the sequence like we can with other architectures. Third, RNNs have short-term memory. They tend to forget information from much earlier in a sequence. And finally, for very long sequences, RNNs become computationally expensive and difficult to train effectively. Once we have all our gradients, the final step is to update every weight using gradient descent. Imagine the loss as a hill, and our weight as a ball sitting on its slope. The gradient tells us which way is downhill, so we take a small step in that direction. We subtract the gradient, scaled by a learning rate eta, from each weight. WXH, Y, and WH all get updated this way, nudging the network to make better predictions next time. Let's see the complete picture. The loss flows backward to the output gradient, then to H3, H2, and H1 in sequence. At each step, we calculate local deltas, accumulate gradients for our shared weights, and finally update every weight using gradient descent. That's the complete backpropagation through time process. Quiz time. What mathematical rule is backpropagation built on? Next question. With sigmoid output and cross-entropy loss, what does dL by dz simplify to? Next question. What is the derivative of the tanh activation function? Next question. Why do we add together the gradients from delta 1, delta 2, and delta 3 for WXH? Next question. What problem happens when gradients shrink towards zero across many time steps? Next question. What is the formula for updating a weight using gradient descent? Last question. Name 2 disadvantages of RNNs. Let's quickly summarize. Backpropagation uses the chain rule to find how each weight affects the loss. Gradients start at the output and flow backward through H3, H2, and H1. Because weights are shared across time steps, their gradients are summed up. Long sequences can suffer from vanishing gradients, and RNNs also have other limitations like slow training and short-term memory. And finally, every weight is updated using gradient descent. That's it for this video. Thank you so much for watching. Now you understand both forward and backward propagation in an RNN, a huge milestone in your deep learning journey. A heartfelt thanks to Ajay sir for his guidance, and to my AI friends, Claudie and Smarty, for their support. See you in the next video.